Chapter 5, Conductors and Overcurrent Protection. This chapter will cover parts of Article 310 and Article 240. Conductors used in electrical systems are often defined by the material, if any, that is used to encase the actual electrical conductor. Three classifications exist for electrical conductors: bare, covered, and insulated. A common element among all electrical insulations is that they provide an opposition or resistance to the flow of electricity. All conductors and cables are marked to identify, among other things, the type of insulation that is used. See Article 310.120a(2). All conductors and cables are required to be marked to identify the maximum rated voltage at which the conductor is listed. The letter or letters necessary to identify the type of wire or cable, the manufacturer's name or trademark or other identifiable markings, and the American wire gauge or circular mill area size of the conductor. The common factors that can contribute to conductor insulation degradation because of excessive operating temperature are listed in Article 310.15a(3). The first factor is the ambient temperature in which the conductor insulation shall operate. The second factor is the internal heat created in the conductor as a result of current flow. The third factor is the dissipation rate of the heat into the surrounding environment. The final factor is the heat generated by the adjacent current-carrying conductors. All of these factors shall be considered prior to selecting the type of insulation and determining the conductor's allowable ampacity. Section 110.5 requires all conductors used to carry current to be copper unless otherwise specified by the NEC. While copper is most extensively used, its cost is a primary disadvantage. The cost of installing electrical distribution systems with copper conductors, primarily in large sizes, can be very expensive. Other factors to consider when installing electrical conductors is the weight of the conductors. Copper conductors installed in vertical raceways require support at shorter intervals than required for aluminum conductors. Section 300.19 lists the required intervals and methods for vertical supports to ensure that the weight of the conductor is not passed on to the conductor terminals. Other considerations when installing aluminum conductors is terminations with dissimilar metals. Conductors of different materials, like copper and aluminum, should not be terminated in a manner that causes the dissimilar metals to come in direct contact with each other unless the termination or splicing device is identified for such use. Conductors for electrical systems are either solid or stranded. Conductors designed for direct physical contact between aluminum and copper are labeled AL-CU and may only be used in dry locations. Solid conductors are constructed of a single piece of wire. Stranded conductors are constructed of multiple wires. The NEC has adopted various color code requirements for many of the conductors used in electrical distribution systems. These requirements ensure proper identification of circuits and conductors, which is critical for the safety of those who are required to maintain the electrical system. Section 310.110 references the applicable color code identification requirements for grounded, equipment grounding, and ungrounded conductors. Subpart A references Article 200.6, which contains the identification requirements for grounded conductors. Subpart B covers the identification requirements for the EGC that are located in Article 250.119. The identification requirements for the ungrounded conductors are listed in Article 310.110c. Essentially, any color other than white, gray, green, or any combination of these colors with distinguishing markings is permissible for the identification of ungrounded conductors. Typically, Typically, the colors brown, orange, and yellow are used as a color identification means for 480, 277 ungrounded conductors, and the colors black, red, and blue are used for 120, 240 and 120, 208 ungrounded conductors. While these provisions do not require these color codes, they permit the use of the color code as one of the means for identification. The color code should never be used as a means for voltage identification. However, by utilizing color coding as a means of identification, the overall level of safety and reliability of the installation can be enhanced for all those who may service or maintain the electrical distribution system. Section 250.119a permits re-identification of the equipment grounding conductors. Number 4 and larger, at the time of installation by a permanent means such as striping the insulation or covering from the exposed conductor, coloring the exposed installation or covering green, or marking the exposed covering or insulating with green tape or green labels. Section 250.119b permits similar methods of re-identification for multi-conductor cables provided the conditions of maintenance ensure that only qualified personnel service the installation. Parallel conductors are two or more conductors that are electrically connected at both ends to form a single conductor. Despite the wide range of conductor sizes available, there may be installations in which it is desirable to use parallel conductors to meet a specific design consideration or installation requirement. See Article 310.10h 1 through 6 for specific rules concerning the installation of parallel conductors. Copper, aluminum, and copper-clad aluminum conductors are all permitted to be installed in parallel. These requirements apply to the individual conductors that comprise a single-phase, neutral or grounded conductor and are not to all of the conductors of the circuit. Parallel conductors are derated per Table 310.15 B3A. Equipment grounding conductors must comply with Article 310.10 H5. Where installed in parallel, however, they should be sized per Article 250.122. All insulated conductors have a maximum operating temperature at which the insulation of the conductor is not adversely affected. Conductor ampacities are directly related to these operating temperature limitations. Table 310.15 B16 lists conductor ampacities for insulated conductors under 2000 volts installed in a raceway, cable, or earth. These values assume an ambient temperature of 30 degrees C and not more than 3 current-carrying conductors in a raceway or cable. While there are many different types of insulations listed, all of them are assigned to be one of 3 basic classifications: 60 degrees C, 75 degrees C, and 90 degrees C. An overcurrent is any current in excess of that for which the conductor or equipment is rated. See Article 100. In terms of application, some equipment is designed to accommodate overcurrents for a period of time depending upon the load. Temporary surge or startup overcurrents are common for some electrical equipment like motors and generally have no long-term harmful effects. When overcurrents occur more frequently or persistent for long periods of time, damage to the electrical system may occur. Overcurrents can result from overloads, short circuits, or ground faults. Overcurrent protection can be selected once the allowable ampacity is determined. Often the calculated ampacity does not correspond to a standard size fuse or circuit breaker. The next higher standard device rating may be used in these cases per Article 240.4b, provided the conductors are not part of a branch circuit supplying more than one receptacle for a cord and plug connected loads, and the next higher standard device rating does not exceed 800 amps. In cases where the cord and plug connected portable loads are supplied by multi-outlet receptacle circuits, and the ampacity of the conductor does not correspond to a standard rating or a fuse or circuit breaker, the next lower standard device rating shall be selected. In installations where the calculated conductor ampacity does not correspond to a standard size rating for a fuse or circuit breaker, the rating of the overcurrent device is over 800 amps, the next lower standard size fuse or circuit breaker shall be selected per Article 240.4c. In the majority of electrical systems, the grounded conductor is the neutral for the system and carries the return circuit current. For this reason, the grounded conductors, in general, are not provided with overcurrent protection. There are, however, two exceptions to this general rule. The first is for installation in which all the circuit conductors are opened or disconnected from the supply simultaneously, and the design is such that no pole can operate independently from another. The second is for motor overload protection as provided in Article 430.36. Some electrical systems, like a three-phase, three-wire, corner grounded delta, operate with a grounded conductor that is normally current carrying conductor. The most commonly used feeder tap rule in electrical distribution systems is the 10-foot tap rule. Section 240.21b1 sets 5 conditions which shall be met to permit conductors to be run without overcurrent protection. The 25-foot tap rule is also commonly used in electrical distribution systems. The major advantage of the 25-foot tap rule over the 10-foot tap rule is the additional length that the conductors are permitted to run without overcurrent protection. To compensate for the additional length, the tap conductor ampacity is more closely matched to the rating of the tapped conductor circuit. There are 4 conditions that shall be met to use the 25-foot tap rule. The 25-foot transformer feeder tap rule is the feeder tap supplying a transformer in cases where the total length of the primary plus the secondary does not exceed 25 feet. This tap rule permits the conductor supplying a transformer to be installed without overcurrent protection at the point at which they receive their supply, provided 5 conditions are met. Subpart 4 contains tap rules for a specific set of conditions in a manufacturing building. Overcurrent protection at the point of the conductor receives its supply can be omitted in the installation for high bay manufacturing buildings with the walls over 35 feet in height. There are 9 conditions that shall be met to apply these rules. Outdoor feeder taps are permitted without overcurrent protection at the tap where the conductors are located outside, except at the point of termination for the conductors. Overcurrent devices shall be installed in a readily accessible location, free from physical damage, and in a location that ensures that all occupants of the building or structure have access to the overcurrent devices protecting the supply conductors for their premises. They shall not be installed near easily ignitable materials or in bathrooms. An overcurrent protected device is used to provide protection from short circuits and overloads. Fuses and circuit breakers are overcurrent protective devices designed to automatically stop the flow of current in a circuit that has a short circuit or is overloaded. Every ungrounded conductor must be protected against short circuits and overloads. A fuse or circuit breaker is installed in every ungrounded conductor. One overcurrent protected device is required for low voltage, single phase circuits, 120 volts or less, and all DC circuits. The neutral conductor in AC circuits or the negative polarity in DC circuits does not include an overcurrent protected device. 2 overcurrent protected devices are required for single phase high voltage circuits, 208, 230, or 240 volts. Both ungrounded conductors are protected by an overcurrent protected device. 3 overcurrent protective devices are required for all three-phase circuits, any voltage. All 3 ungrounded conductors must be protected by an overcurrent protective device. All plug fuses shall be marked to indicate their ampere rating. By design, the plug fuse ampere rating is identified by the shape of the window on the fuse. Plug fuses with ampere ratings of 15 amps or less have a hexagonal window, while those with ratings greater than 15 amps have a round window. The 2 basic types of plug fuses are the Edison base fuse and the type S fuse. Cartridge fuses can be constructed with a ferrule or knife blade construction. Both of the types are inserted into fuse holders, which make the connection from a line to the load. Non-time delay fuses are fast-acting and provide excellent overcurrent protection. Time delay fuses are designed to be used with utilization equipment, like motors, that are subject to temporary startup or surge currents. Time delay fuses allow overcurrents to exist for short periods of time to avoid nuisance tripping due to equipment startup characteristics. Thermal circuit breakers contain a spring-loaded electrical contact which opens the circuit. The spring is used to open and close the contacts with a fast snap action. The handle is added to the contact assembly so the contact may be manually opened or closed. The contacts are automatically opened by an overcurrent by a bimetal strip and or an electromagnet tripping device. The contacts have 1 stationary contact and 1 movable contact. The movable contact is attached to a spring that provides a fast snap action when tripped. Inverse time circuit breakers are used extensively in electrical distribution systems and for many different types of applications. They are available as single, 2, and 3-pole configurations. ITCBs provide protection from normal overloads and against damaging currents from short circuits and ground faults. This is accomplished by a thermal magnetic circuit breaker by using the thermal element for the overload protection and the magnetic element for the short circuit and ground fault protection. All circuit breakers shall clearly indicate whether they are in the open or closed position per Article 240.81. The open position is off and the closed position is on. For vertically mounted switches, the on position of the circuit breaker shall be up. Circuit breakers shall be marked to indicate the ampere rating, the interrupting rating, and the voltage rating of the device. Additionally, circuit breakers which are permitted to be used as switches shall be marked to indicate such use.